Okay, students, this is, I guess, the back page of your review, the left side. First of all, I apologize it's so small. So if you need your own piece of paper to write extra stuff down, that might not be a bad idea to do that. Plus, you'll probably start using that piece of paper as your notes card for your test. Might be a good idea, actually, to write things down on their own. So we start with finding inverses. Okay, remember, this means inverse function. Find the inverse function. F, it's not f to the negative first power. Okay, this means the inverse. Okay, and the inverse is, of course, what you get when you switch your x and your y values. Okay, and then solve for y again. So for these first two, it asks you to find the domain, but it's not really that important because both of these are linear functions, so they have all real domains. Okay, the domain part is basically for 3 and 4. So with all things inverse, you switch your x and your y, and you solve for y. Remember, f of x means y. So you put the x in the y position, and you put the y in the x position. And then you solve for y again. So we'll solve simply by adding 4 to both sides. So x plus 4 equals y inverse. So the last thing to do is to write the little -1 above your y to indicate that we are finding an inverse of some other function that we began with. Okay, so if y equals 4 plus x, then the inverse, y inverse equals 4 plus x. Yep, that's it. Okay, on this one, once again, you start by switching your x and your y's. So x equals 1/3 of y minus 5. Okay, and we do all of our math to get y by itself and then rewrite it as y inverse. So if you notice, anytime we have a linear function, we're going to have a linear inverse. Right? The inverse of a line is another line. Okay, as opposed to what we're about to do here on 3 and 4. Both of these are square roots. Okay? So if we have a square root function, the inverse of a square root function is half of a quadratic function. Okay? Only half of a quadratic. A normal quadratic would have a whole entire u. Right, a left side and a right side. But your graph to begin with only has a top side, which means we can't have the entire thing, which is why the domain comes into effect whenever we have a square root function. Because we don't get the entire quadratic, we only get half of the quadratic. So we have to limit our domain. And I'm going to show you how it is that we do that. Okay, so first, let's practice finding the domain here for number 3. For the domain, we know that you cannot take the square root of a negative. At least I hope you know that. So you take whatever is underneath your radical, the x plus 3, and you make that so that it can't be negative, right? Bigger than or equal to 0. This is how we find the domain of your square root. It doesn't use the -2, right? That's not important for the domain. The domain is only underneath your square root. So we can only use values greater than -3. So as an interval, that would be from -3 to infinity. Okay? Because greater than or equal to has a bracket. So you're going to put a bracket on there. Now what about the range? If this is the domain, then the range is given to you by this number. Okay, right? This is a vertical transformation, so it moves your graph down 2 units. So the range of this would be y is greater than or equal to -2. Okay, so a range from -2 to infinity as an interval. Okay, and that's going to come up here again, because remember, when you switch your x and your y's, the domain of what you start with becomes the range of your inverse. And the range of your inverse becomes the domain, the range of your original becomes the domain of your inverse. So actually, this one is more important to us for our purposes. So let's go back and actually find out what this equation is. So here's your equation, root x plus 3 minus 2. So we're going to switch your x and your y to begin with, like we always do to find an inverse. So x equals root y plus 3 minus 2. Okay, switch your x and your y's to start with like we do for every inverse. And now we do the easy stuff first. So we're going to add 2 to both sides. X plus 2 equals square root y plus 3. And now we have to deal with our square roots. How do you undo a square root? Well, we square it. So we put a little 2 here, and you put everything in parentheses, and you put a little 2 there. Okay? We don't square each individual thing. You square one on the left and everything on the right. So this one all gets squared together. This all gets squared together. So the 2 and the root, right, the square and the square root cancel each other out. And you don't have to multiply that out at all. Okay, there's no reason to square the x plus 2. Okay, this is not what we're trying to find. So our last step is minusing 3 from both sides, and that happens outside of your parentheses. Remember, so we have y inverse, or in this case, h inverse, because our original function was called h. So we could have an h inverse here also instead of y inverse. It's x plus 2 quantity squared minus 3. Okay, but remember, that's the whole entire u. That's the whole entire graph of our quadratic. And we can't have that. We can only have the right side. Okay? So we're going to come up here and look at our domain. Remember, our range was y is bigger than or equal to negative 2. So we have to put that in down here as your constraint. We have to have a domain constraint. X is bigger than or equal to negative 2 in order to only have the right side of your graph. Okay? We are not allowed to do any sketching on the left side of your graph because your square root didn't have a full u, so your inverse can't have a full u either. Okay? And this is the part that you need to remember for your test. Okay? That anytime you're figuring out an inverse of a square root, okay, the inverse of a square root is a quadratic. But you can't have both sides of your quadratic, so you have to restrict the domain to only the right side in this case. Okay, so let's see if we can apply that same type of an idea to number 4. Okay, find number 4's domain and find number 4's range. Actually, let's just find the range. Let's just do that. What is the range of this function? And it always comes from this. So the range of our function is y is greater than or equal to 3. Okay? Because this is a 3 units up vertical transformation. So what used to be at the origin is now 3 units up. Okay, the other transformations, this makes it open to the left. Right? The negative x means you have a y-axis reflection, so it opens left. And then the minus 1 means it goes left 1. If your x is negative, then this is true. Negative x means this goes left. It obeys its sign if x is negative. So it goes left 1, 3 up, and then it opens to the left also. Okay, so let's sketch that real quick. So let's get to finding the inverse. So x comes over here, and your y is underneath your radical. Okay, so simple stuff first. We subtract 3. And then, of course, we're going to square both sides. So the square goes here, and you put parentheses around your x minus 3, and you square that also. So x minus 3 squared equals negative y minus 1. Okay, negative y minus 1. So we're going to add 1 to both sides. plus 1 equals negative y, and then we're going to divide both sides by negative 1. Okay, so we're going to change all the signs. Y inverse equals negative of x minus 3 squared minus 1. Right? If I make this whole entire thing negative, that means the parenthesis gets negated and that thing gets negated. Both of those become negative. Now I have to put in my domain restriction, which came from the other thing's range. So as long as x is bigger than or equal to 3, we're going to be good. Okay, so this is the complete answer. Whenever we start off with a square root as your function, you're going to have a quadratic with a domain restriction as your answer. Okay? Whenever you start off with a square root function, you're going to have a quadratic with a domain restriction as your answer. So our next two questions are asking us a similar type thing. For each function, find a domain on which f is 1 to 1. Right? That means every y value comes from exactly one x value and non-decreasing. That means it can be 0 or increasing. Okay? So let's talk about what that means. Here we have a function, f of x equals x plus 5 squared. Okay? So talk about the transformations here. The plus 5 means we're moving your graph 5 units to the left. Our graph goes 5 units left. Okay, so let's graph that real quick. So notice all the way here, our graph is going down from left to right. So our graph is decreasing. It says we don't want our graph to be decreasing, do we? It says we want our graph to be non-decreasing. So we can't include any of this stuff all the way to there, right? All of this stuff here is decreasing. We want it to be non-decreasing, which means we can only start here at this point. So we have to limit our domain to something bigger than negative 5, because that's the vertex of your quadratic. Okay, so that's what we do first. We're finding a domain restriction so that now if you draw a horizontal line, there's only one side of your quadratic to run into. Okay, and applying the horizontal line test, if it only crosses once, that means your function is 1 to 1. And if your function is 1 to 1, that means the inverse exists. Okay, so we are changing your equation's domain so that we can make this a 1 to 1 function, and we have a something we can actually find the inverse of. So as long as we restrict the domain to bigger than or equal to negative 5, then this is fine. Okay, but we have to restrict it first. So now that we've done that, we put your x value over here and your y value in here, and we solve. Okay, solve for y. So we square root both sides, bada bing, bada boom. Root x equals y plus 5 minus 5 and junk. So the inverse of our original graph is root x minus 5. Okay, root x minus 5. And notice the domain here, right, is the same. So as long as the range is now minus 5, x has to be bigger than or equal to 0. Okay, so in order to get the inverse of a quadratic, we have to adjust the domain so that the inverse exists. Because if your graph or your function is not 1 to 1, then the inverse does not exist. And a quadratic by itself is not 1 to 1. So we restrict the domain, right? We find out where the vertex is, and you chop off the left side in order to make your function 1 to 1. Okay, so that's the why. Why are we asked to find a domain so that it works? So for this one, what does the minus 8 do to our graph? Hopefully you know it moves it down 8 units. Okay, so what is the vertex? What is the x-coordinate of my vertex? Well, that's going to be 0. So as long as I restrict my domain to everything bigger than or equal to 0, I am not able to graph the left side, and therefore my quadratic will be 1 to 1. Okay, so I have a domain restriction of 0 or bigger in order to be able to find the inverse, because I can't find the inverse of something that is not 1 to 1. So we restrict the domain in order to have a 1 to 1 function. And that is going to be your answer. Okay, so sticking with the inverse theme, here we have an F and a G, and it says find F inverse and G inverse. Okay, so let's do that. 2 linears will give us 2 linear inverses. Okay, and then the next part asks us about compositions. It wants f of g of x, which means take your g equation and plug it into your f function. Half of 3x plus 6 minus 2. Okay, so when we do that, we get something that's not exactly gorgeous. So 3 halves of x plus 3 minus 2, right? Plus 3 minus 2 is a plus 1. So we get this as the composition, f of g. Okay, and then if we do g of f, right, that's the other way. That's taking the 1/2 x minus 2 and plugging it into there. 3 1/2 x minus 2. I told you there wasn't a whole lot of space here. Plus 6, that's once again 3/2 x minus 6. Minus 6 plus 6 is 0. So this is f of g of x. Okay, now it says, what does this tell us about the relationship? Well, not a whole heck of a lot, but what it does tell us is that f and g are not inverses of each other. Okay, I guess that's the only thing it's supposed to tell us. F and g are not inverses of each other, because if they were, each of these things would simplify down to x. Okay, so f of f inverse always gives you just x as the answer. So if two functions, when you compose them, give you x as their simplified answer, that means those two functions are inverses. Okay? So if, when you compose them, they simplify to x, that means those two are inverses. So even though these two aren't, I think that's what I was trying to get at with that problem. Okay, so we have now upped our game, and we want to find the inverse of this rational function. So you put your x value there and your y value down here in the denominator. Okay, so I'm going to try and work in this area and see if it works. So y is in the denominator. I have to move it out of the denominator. I do that by multiplying. Multiply both sides by 3y plus 2. Okay, that cancels out the entire thing, 3y plus 2. Okay, so now we have that over here. And there are two ways, so you have to make a choice. What do you want to do with this parentheses? So one choice is distribute. The other choice is divide. Now in this case, distributing is easier. I'll show you divide in a second. So 3xy plus 2x equals 2. Okay, we will move the 2x over there to that side. 3xy equals 2 minus 2x, right, because it's the opposite. And then we're going to divide both sides by 3x. Okay, so we can write this as one thing with the correct notation. Y inverse equals, or f of x, f inverse, 2 minus 2x over 3x. Okay? So oftentimes when we start off with a rational equation with x in the denominator, we end up with another rational equation with x in both places, the numerator and the denominator. Okay, and then the last problem on this page, is this even, odd, or neither? Well, we take a look at the symmetry, and if I draw a line right down the middle, does the left side match up with the right side? The answer is yes. This is even. This is an even function because it has y-axis symmetry. Okay, we talked a little bit about this in the first video. From a graph, how do you know if it's an even function? Well, you look at its symmetry. The left side is exactly the same as the right side. Okay? And this question isn't supposed to say that. It's supposed to say, does the inverse exist? Okay, and the answer to that question is a resounding no. If you draw a horizontal line through your graph, it hits it more than once. Okay, so no, the inverse does not exist because, right, the graph of f is not one-to-one. It fails that horizontal line test. Okay, so this page is all about inverses and domain restrictions and other things that we're doing in order to be able to write an inverse. Okay, so remember, if your function is not one-to-one, then the inverse does not exist. That's an important concept to know. All right, see y'all on the next video.